Hello, in this video we will see about using IQ modulator as a RF phase shifter. In this presentation we will see about realization of voltage controlled RF phase shifter using IQ modulator and some common lab equipments. Then we will see the theory behind the working of the phase shifter. Then we will establish relationship between control voltage and the phase and amplitude of output wave. Then we will see LabVIEW simulations and a simple implementation code for our phase shifter. Following equipments are used to build this phase shifter: a single channel arbitrary waveform generator or RF generator, and then we need an IQ modulator, and then we need DC dual channel bipolar power supply or a source measure unit. Bipolar means both positive and negative voltages can be applied in the same channel without having to switch the connections manually. And finally, we need a PC to control our DC power supply. This phase shifter can be used for laboratory and scientific applications, and it is used to compensate the limitation of RF generator with only one channel, in which part of the single channel output can be relatively phase shifted to the other. Here is a simple block diagram for the voltage controlled phase shifter. The input reference signal from a single channel arbitrary waveform generator is represented as A cos omega t, and this signal comes here to the power divider, and the value of A ref and AI depends on the ratio of the power divider, and it can be measured using an oscilloscope. The AI cos omega t wave component serves as input to the voltage controlled phase shifter. The output amplitude A0 and the phase phi of the output signal can be controlled by the voltage applied to the phase shifter. The main requirement of our phase shifter is that the input and output both should have same frequencies omega t. The main concept behind this phase shifter circuit is how a single signal from the waveform generator can be split into two, whose amplitude and phase can be controlled relative to one another based on the voltage applied to the phase shifter. In the next slide, we will see about the setup in implementing the voltage controlled phase shifter. Here is the overview of the setup in implementing our phase shifter. It consists of IQ modulator and a dual channel bipolar DC power supply and PC with LabVIEW or Python. DC power supply has two channels and it produces output VI and VQ. VI stands for voltage in phase and VQ stands for voltage quadrature. And in the upcoming slides we will see how IQ modulator works and the relationship between VI, VQ and A0 and phi, and how to generate the required output signal by controlling the DC power supply using LabVIEW. This is the block diagram of IQ modulator. It takes in local oscillator LO, VI and VQ as input and produces a resultant output. This is the circuit diagram of IQ modulator. The input waveform AI cos omega t shown in the previous figure comes here as a local oscillator input, and part of it goes as in-phase component to this RF mixture. The other part is 90-degree phase shifted and goes as quadrature component to this RF mixer, and both are multiplied by VI and VQ respectively and finally combined using RF combiner to give this resultant waveform. In the next slide we will see how to visualize and solve this resultant waveform. IQ modulators are mostly used in communication technology like QAM and QPSK. For more information, see the links below. So here is our resultant waveform from the previous slide. Our in-phase DC voltage is multiplied with the in-phase wave component, and our quadrature DC voltage is multiplied with the 90-degree phase shifted wave component. The resultant waveform can be represented as the real part of the complex identity. And here is the magnitude and here is the phase of the wave. If we take the ei omega t component, which is common for both the terms outside, we will be left with these terms inside. Such complex terms can be represented by a phasor diagram in which the phasor arrow rotates at a constant angular velocity omega, and the waveforms can be generated from the phasor diagram by projecting the vector magnitude along x or y axis. The complex in-phase wave component can be represented using this phasor diagram, where AIVI is the magnitude of the wave and omega is its angular velocity and the initial phase is at 0 degree. Similarly, the quadrature waveform can also be represented by this diagram, where AIVQ is the magnitude and the phase is 90 degree relative to AIVI. Now both the phasor diagrams can be combined into one, and the resultant waveform can be drawn, with A0 being the magnitude of the waveform and phi being the relative phase shift between the in-phase and the resultant component. The magnitude of the resultant component is given by AI square root of Vi squared plus Vq squared, and the phase is given by tan inverse of AI Vq divided by AI Vi. Since A0 and phi are the required output, we need to establish relationship between Vi, Vq, phi and A0, which can be easily obtained from this diagram by simply projecting the A0 component along the x-axis would give rise to AIVI is equal to A0 times cos phi, as shown in this equation. Now we can calculate Vi, which is A0 divided by AI times cos phi. Similarly, the magnitude of Vq can be found by projecting A0 along the y-axis, which leads to AI Vq is equal to A0 sin phi, and finally Vq is equal to A0 divided by AI into sin phi. Since that we have established the relationship between Vi, Vq, A0 and phi, we will now see an animation to fully understand this one. Now we will substitute A is equal to 1 in the previous equation in order to make it easier for us to visualize the equation. Here we could see how the relative change in the Vi and Vq magnitude give rise to the resultant magnitude represented here by the green arrow. So here is the corresponding wave diagram. Here is only the magnitude of Vq and Vi is changed, and which results in the relative phase shift of the resultant component. So that's how simply by changing the magnitude of Vi and Vq we could achieve a resultant wave of different phase. Here is an example using actual voltage and phase value. Again we will take the equation from the previous slide and assume AI is equal to 1. You can change the value of AI to the desired value by changing the amplitude in arbitrary waveform generator or by using the power divider of different ratio. If one needs output of amplitude 1 and phase 0 relative to the I waveform, then one has to substitute the amplitude A0 is equal to 1 and phase is equal to 0. So 1 times cos of 0 is 1, so the Vi value is 1, and Vq is equal to 1 times sine of 0. Sine of 0 is 0, so Vq is equal to 0. Let's take another example. If we need an amplitude of 1 and phase of 180 degree, then we have to substitute 1 here and 180 degree here, which would give rise to -1, and VQ value will be sine of 180 degree is 0, so VQ is 0. So by using this formula, one could create a table with required output, amplitude and phase, and the required input of VI and VQ. Here is some additional notes or information related to the phase shifter. The phase resolution also depends on voltage resolution of DC source, noise from arbitrary waveform generator, etc. If one has high voltage resolution, then this will result in high phase resolution of our phase shifter. IQ modulators have a specified carrier frequency and I and Q frequency bandwidth. So when one is buying an IQ modulator, they should be aware if the required output frequency is within the specified carrier frequency range of the IQ modulator. And if we could apply a DC voltage as I and Q input. IQ modulators have losses that must be accounted for by including a loss factor LF shown in this equation. This loss factor helps in compensating for the loss in amplitude of the output waveform. Cable length, reactive and active circuit elements may cause some phase error that must be accounted for by adding or subtracting a constant delta phase error in the phase term through calibration. One should also note that the loss factor could depend on the phase. In that case, the Phasor diagram won't be circular, but it will be elliptical. Such errors can be easily compensated by applying a loss function that depends on the value of phi. It is important to do calibration before using such phase shifters by observing the output using an oscilloscope. Normally, such errors would be minimum if one buys an IQ modulator of good quality. Finally, one could reduce LF and AI into a multiplicative factor, MF, that could be multiplied to our equation to get the required amplitude and phase. Now we will see a LabVIEW simulation and an example implementation code of our phase shifter. It consists of one simulation VI and then one example implementation code using 2-channel Keithley 2600 source measure unit. You can see the link below for the LabVIEW VI files. Here is our LabVIEW simulation. The white waveform represents the input reference waveform and the red waveform represents our output waveform. Here you could change the phase and amplitude of our output waveform. Here one could add the phase error and the loss factor. Now we will go ahead and run this simulation by pressing run continuously, and then we could change the phase of the output waveform related to the input waveform. Also we could change the amplitude of the output waveform relative to the input reference waveform, and then press stop to end the simulation. Now we will go ahead and see the block diagram of our phase shifter. Here we have the quadrature waveform generated by using a signal generator, and then it goes to the RF mixture, which is a simple multiplier, and similarly we also have an in-phase component cos omega t, which also goes to the RF mixture, and the part of it goes out as a reference waveform. Here is our input to our phase and phase error. It could be added or subtracted based on the amount of phase error, and then it goes into degree to radian converter and then is provided as input to sine or cosine terms. Here we also have amplitude term on the last factor. Both are multiplied and goes here and gets multiplied by the respective sine or cosine term. This results in quadrature DC voltage and in-phase DC voltage multiplied by their respective component in their RF mixture and finally combined using RF combiner and given into the waveform graph, which we see in our front panel. Now we will see a LabVIEW implementation code which is similar to this simulation code but has some additional VIs for Keithley source measure unit. Here is the input to our SMU unit, which we could select it if it is connected to our computer. Then we have to select our required phase and the required amplitude of our output waveform and their corresponding phase error and the loss factor, which would be converted into the input voltage for our SMU unit. Now we will go ahead and look at the block diagram of this VI. Here one could see that the top part is similar to our simulation VI and the bottom part corresponds to our SMU unit. Our SMU unit is defined in such a way that channel A corresponds to the in-phase DC voltage and the channel B corresponds to the quadrature DC voltage VQ. First, our Keithley source measure unit is initialized using this VI and then channel A and channel B are set to source voltage and then the voltage level for channel A and channel B are taken from their corresponding output from the simulation. Finally, channel A and channel B outputs are enabled and then the SMU is closed. So this is how the set output phase and amplitude is converted into the respective input voltages for our DC SMU power supply. Finally, we will see the summary on how our phase shifter works. The input reference signal from the arbitrary waveform generator A cos omega t is divided into two parts by the power splitter, and the one component serves as input to our phase shifter, which is an IQ modulator. AI cos omega t goes to this RF mixture as in-phase component, and the other half is 90-degree phase shifted and goes as quadrature component to this RF mixture and then gets mixed with VI and VQ DC voltages based on this equation, which is obtained using the output amplitude A0 and phase phi of the output wave, which is calculated by the LabVIEW program running on this computer and gives it as input to the DC power supply. Finally, the mixed signals are added using RF combiner that gives rise to the required output wave of amplitude A0 and phase phi. Thank you. If you like this video, please comment, like, share and subscribe. See you.